Okay, good afternoon. We're going to continue on with our discussion around acids and bases. So welcome to the last class of week one. We made it, guys. 1 week down, 16, 20 or so to go. What we're going to do today is review a little bit about some of the definitions we started into and then continue into calculations. So these are the calculations that are going to be necessary for things like the acid-base assessment. Should be online now. Where we left off last is we started discussing this idea of what are called non-innocent ions, right? If salts are dissolved into water, there's a possibility they will participate in changing the pH of the solution. Really what we're saying about changing the pH, again, what defines pH? If we say the pH is changing, what is that synonymous with? What has to change for the pH of the solution to change? Yeah, the hydronium ion concentration has to change. Exactly. So because of that, what we're really saying then is that we have to somehow increase or decrease the concentration of the hydronium ion, and then that's going to mean that we are somehow basically adding an acid or base to the solution, right? Either we're going to be increasing the hydronium ion concentration, adding protons, or decreasing it somehow. And so we classify ionic compounds as one of these two sort of characterizations. Either they're going to be in solution and innocent or non-innocent. So the two situations we were talking through last was lithium chloride, and the second one we were going through was potassium acetate, where in this case it's CH3 COO as a species. So there's two important skills to go through with this part. First, for any compound that is given, for any molecular compound, you need to be able to recognize what part of it makes up the ion. In other words, how to split it up into its representative cationic or anionic components. So what you're looking for is cations are going to be things from the very extreme left hand of the periodic table. Something that is anionic will be usually from the right hand of the periodic table. So lithium chloride will, when it's in water, dissociate into our lithium plus, chloride minus. Whereas the potassium acetate, that's going to dissociate into our potassium plus, and then acetate, this more complex molecular anion, COO minus. So that's first, being able to split these things into the representative ions. Next is looking at these ions. What you're on the hunt for is, are any of these ions conjugate acids or bases of some weak acid or base that we have discussed, right? So what I mean there is, okay, lithium right now, that is usually the counter ion, or where we would normally see this in the context of acid-base chemistry, that would be something like lithium hydroxide. Again, I'm giving it this hydroxide because lithium is positive. Hydroxide is the species that we'd be using to balance against it. Again, this is just remembering that if I've got sort of a cationic species, it's normal under any other circumstance. If I was going to throw it into water, ionically it will balance against the anionic species present, which would just be hydroxide. That is not a weak acid or base, meaning that this lithium is not the conjugate acid or base of some weak acid or base. The same is true about potassium. Both of these cases, these positively charged species would generally be pairing with hydroxide. Those would both be strong bases in our normal organization. Chloride is something we've seen before in the context of acids and bases. Again, if we look at chloride, since it is anionically charged, we would generally pair that with a proton. So H3O plus, meaning that if I was going to associate this, I'm just acting where this species has to act like an acid or base, chloride would accept a proton to form HCl and H2O. So as I've written this equilibria, let me convert this to an equilibria. In the way that I've written this equilibria now, I'm just going to assign their roles. Chloride, as I've written this, going from left to right, what is chloride's role? Imagine this equilibrium has to happen as drawn. If chloride over here on this side is forming HCl, yeah, it is a base making HCl what? If that is my base, HCl would be considered, yeah, that's right. This would be the conjugate acid in this case. Now remember, having something being called a base and conjugate acid, that's just saying that they are part of a conjugate acid-base pair. That's how they are related to each other. Whether or not something is called a conjugate acid or just an acid is really just a point of perspective. Staring at the chloride on the left-hand side, I say it is a base, making HCl my conjugate acid, but the reciprocal is also true. HCl is my acid, making chloride my conjugate base, right? So both of those two statements are correct. If HCl is considered the acid, chloride would be its conjugate base. And again, we look at that. Yeah, I've seen HCl. That is actually a strong acid. Therefore, chloride is not the conjugate base of a weak acid. It is the conjugate base of a strong acid, and thus will not have any impact in the system. So that's how we go through and eliminate species as innocent. If it is an ion, which is normally the conjugate acid or base of a strong acid or base, there will be no impact by putting it into solution. This is our guy that has something that will do something. If anybody recognizes this. So once again, let's use this test in terms of sort of identifying it. CH3COO-, the name of that is acetate. It comes from, it has this ATE ending, the anionic species. You guys should recognize that as what? What equilibrium have you seen that, or where, if this is added to a solution, what is the normal species we've already discussed in class so far? CH3, COO-. We've seen this as, acetic acid. Normally, it would be from the acid-base equilibrium of acetic acid. We recognize acetic acid, and acetic acid is a weak acid. Therefore, acetate is a conjugate base of some weak acid. Meaning, again, that means that acetate is part of an acid-base conjugate pair. Its conjugate is this weak acid. It is the conjugate base of a weak acid. That is where your sort of alarm bells go off. This is a species who will affect this equilibrium. Now, in terms of which direction the equilibrium will go, how the pH will change, what I'm really saying, and I add potassium acetate to the solution, I'm not weighing out and adding acetic acid. I am adding potassium acetate. I'm adding this part of the equilibrium, right? Which means I am adding what? It is not a weak acid I am adding what to this solution? I'm adding a weak base. Yeah, I'm adding the conjugate base of a weak acid. But that's the key statement to focus in on. I am adding a weak base to the solution, or I'm adding the conjugate base of a weak acid to the solution. I am adding a base. That's the thing. You're right. You are dissolving salt. That is true. But that salt is composed. One of the two ions of that salt is the conjugate base of a weak acid, meaning it will act like a base. So, adding this, which is a base, we expect the pH to what? Increase or decrease? Yeah, it will increase. And again, just from a perspective, I am adding a weak base or a conjugate base of some weak acid to the solution. But I'm not, remember, the point to keep in mind, I am not adding acetic acid. I'm adding the fragment that acetic acid is related to, its conjugate. And as a result of that, I'm adding a base. Adding a base must increase the pH of the solution. Now let's do the same assignment or assessment on the last ion. The last ion we had here was this methyl ammonium bromide. So it's CH3, NH3, Br. So splitting this to the representative ions. Again, this is our prototypical anion, something from the halogen series. That's Br minus. And we have CH3, NH3 plus. Does anybody hedge a guess, IUPAC name? What would you call this? CH3, NH3 plus. what might you give it as a name? Again, going back to the last couple lectures, we talked about a similar kind of species, a nitrogen plus species. Do you remember what the name of that was? If this was NH4 plus, what would I call that? Not ammonia. Ammonia, right, is NH3. That's the neutral form of this nitrogen species. Yeah, positively charged. NH4 plus, we call this ammonium. It's got the onium ending to it. All right, so it's not ammonium. Yeah, 1-methyl ammonium. That's a good guess, exactly. It's not just ammonium. It's got this group on it, the CH3. It's going to have this methyl or an alkyl name to it. That's right. So, but point is, it is related chemically, even though it doesn't look exactly like it, it's very similar in species to this guy, NH4+. Now again, back to where we've seen it. Where have you guys seen ammonium, NH4+, in the context of acids and bases? What is it? It is the conjugate what of what? It is the conjugate. So remember, the things we're talking about, NH3, NH4, that's the conjugate acid-base pair. So ammonium is the conjugate, it is the conjugate acid of NH3. It differs by 1 proton as compared to ammonium, which means, again, if by that same sort of logic, if I have CH3, NH3 plus, likely what's it going to be doing? Is it the conjugate acid or conjugate base of something else? If I have to find out like who he's related to, okay, if this was the conjugate base, that means what? Well, it will have a conjugate base. That's true. This is not a conjugate base. This is the conjugate acid of, the other side of the equilibrium would be CH3NH2. It is the conjugate acid of this species less 1 proton. Because again, if we were to set this up as an equilibrium, going through this equilibrium, I have an extra proton, I'm losing that proton. As I go this way in the equilibrium, it is acting like an acid, right? So, it is the conjugate acid of this species over here. Now, what did you remember about ammonium, or ammonia, NH3? Was that a weak base or a strong base? Yeah, that is a weak base. So looking back at the first pair, NH3 is a weak base, meaning NH4 plus is the conjugate acid of that weak base. The same is true with any ammonium species. So ammonium or methylammonium or ethylammonium, as we change this carbon group here, that there, the same properties apply. This is a positively charged nitrogen species. That's why it has the similar name. It is an ammonium, which means it is still a conjugate acid of some other species. And more importantly, these nitrogen species, just like ammonia, are all weak bases. So, this species here, yes, first of all, what is it related to? It is the conjugate acid of some base. We recognize that because it has an extra proton, this positive charge, meaning it wants to get rid of that positive charge, become neutral, meaning it's acting like an acid. This is a conjugate acid species. It is weak because nitrogen, NH2, neutral nitrogen complexes are sort of category of prototypical weak bases. So now, again, back to our final part. If I'm adding this species, the CH3, NH3+, it is a conjugate acid. What do I expect is going to happen to the pH? I am adding a conjugate acid to the solution. Therefore, the pH of that solution will go what? Up or down? Yeah, I'm adding an acid to this solution. Exactly. So, the 3 species here, lithium chloride, both of the 2 components, lithium and chloride, they are innocent ions. They are only related, we've only seen them in the context, or they are part of strong acid bases. Nothing happens with either of those components. The second example, potassium is part of a strong base. Last one, bromine is part of a strong acid, which means I am adding the salt, the conjugate base of some weak acid in the second example. I'm adding the conjugate acid of some weak base in the third example. I'm adding a base in the second, an acid in the third. That's how the direction of the pH changes. So what we're trying to emphasize here is leading up to what we've been discussing about acid and base buffers. Again, one just a thing to note down, for as far as your context goes, R. Does anybody know the terminology R? So if I write R, COOH, do you know what I mean by that?
Functional group?
Yeah, it's the rest of the molecule. Organic chemists are lazy and they like to use abbreviations. R is a shorthanded way to say anything else, usually carbon, but it's anything. It is a generic thing, right? So what we're saying is, if I have any molecule where this, and we've got that part, what we're trying to do is emphasize this part of it. These guys are called carboxylic acids. And they are always weak acids. They are what we will go to talk about the properties of weak acids. No matter what that R group is, they are all weak acids because of that COOH functionality. In the same way, if I have RNH plus, so some species, which means at least, remember, does everybody remember the bonding order for nitrogen? How many bonds does neutral nitrogen normally have? Yeah, it has 3, which means if I have something that is, I'm just going to denote this as R1, R2, R3, 3 things. I don't care what those are. Those could be hydrogen, those could be carbon, but they're just the rest of the molecule. The business end of it is this part here. NH plus, that is a prototypical. First of all, what do you think this is? NH plus, would this be a conjugate acid, a conjugate base? If it is something that is nitrogen with a hydrogen plus, what do you think that is? Yeah, that's an acid again. I have an extra proton. These guys again will be weak acids. Why? Because it is the conjugate acid of something that looks like this. R1, R2, R3. These guys, does anybody know what the name, like we said before, this here, what do you think the root name of a nitrogen plus species is? Any NH plus species? No, not an amide. What was the name of this? NH4 plus, we called that ammonium. Yeah, these are ammonium salts. Ammonium being where the R groups could be methyl, could be ethyl, could be the rest of the fruit. But they're an ammonium salt. They're an ammonium cation. Meaning this guy here, these are amines. The neutral form of it is an amine. So amines are our typical weak bases. Likewise, what we finished up here, these carboxylic acids are our typical weak acids. That also means that if I had its pair, RCOO minus, these are going to be what? If my RCOOH is my prototypical weak acid, what do you think RCOO minus is going to be? Same mirror as we did there. Yeah, these guys are going to be our weak bases again. They're still related in this conjugate acid-base pair. Carboxylic acids will have these acetate or carboxylate ions. That's your acid-base pair there. Carboxylic acid is the weak acid. The carboxylate, the negatively charged species, is its conjugate base. Amine species are our prototypical weak bases. Ammonium species, the NH+, are our weak acids, the conjugate of these guys. So these are the ones you should know on sight. When you see them as part of a salt, they will respond. They will be part of it because you're adding that piece of the reaction. So this is why it bridges over to buffers. So first of all, do you guys remember what is the name, or what is a buffer? So this is what, again, this is the definition, but if you had to give your own name to it, where have you experienced or heard the term buffer before? What have you experienced as far as a lab, or do you guys have any way of if you had to explain this to somebody, to your mom? Is an indicator? No, remember, well, you're right. A lot of indicators are buffers. Yeah, blood work is where you see it typically. But yeah, that's the definition right there, Dylan. It resists pH change. It acts like a chemical battery. Its job is, if you have a solution that really you do not want its pH to change, you have to have this buffer in the solution, and its job, if that solution gets protons added to it, the buffer's job is to hold on to or take up some of that capacity. So likewise, if a base is added to a solution, the buffer's job is to give up some protons. Its job is to really try to maintain the overall concentration of free H3O plus in a solution so that the pH does not change. Graphically, you can think about this, again, I like to think about it kind of like a battery. If you had a solution where the pH is equal to the concentration of your H3O plus, that's the thing you're really watching. So if you imagine a beaker, and I've got something and some other component. Every single buffer, well, I'm not going to give it a charge. Just imagine I've got these two species. These are the two components I have. Every buffer must be made up of an acid and its conjugate base. And they're always going to be a weak acid and its conjugate, or a weak base and its conjugate. You must have two components in the system. And the reason why is because if this solution, what I'm trying to do is I've got H3O plus floating in solution. If I add external H3O plus, well, what that would normally do is it would increase the concentration of H3O plus. Having these guys in solution though, this H3O plus added, what's going to happen is the blue guy, acting as the base, will react with it. And when a base reacts with H3O plus, what does it form? If a basic species reacts with, okay, you're right, a base reacts with water, that's true. That's only true if what is that base? Water can only be the product between an acid-base reaction if you're using a hydroxide, right? That is only true if you take hydroxide and react with this. So that's true. That absolutely will neutralize. That's great. What we're doing is using a base, something we're just going to generically call B. When that base, B, so writing this out, equilibrium, if some base reacts with H3O plus, I make base H plus and water. You're right here. This is that sort of free water. What do I call this? BH plus is, well, salt, but no, remember, back in the context. Yeah, it is the conjugate acid of that base. A buffer works because I have these two parts of this critical equilibrium. I have both the conjugate acid form and the base form. Another way to write this is if I was using a different kind of buffer. Let's say HA plus water gives me a minus and H3O plus. These equilibria are what are going on inside a buffer, where the two components, right, is you've got some conjugate acid and some base in this weak acid-base conjugate system. That's what makes up a buffer. They have to be this molecule pair that is only related by plus or minus one proton. And because of that, if we're having both of them together, this becomes a sort of an equation where by Le Chatelier, if I add hydroxide to the solution, I'm going to be reacting some of this. So I'm pulling on this side of the equilibrium. But because I've got the buffer in solution, if I pull this equilibrium this way, because hydroxide is kind of trying to chew up the H3O plus, what happens to the concentration of this BH? the concentration of BH, if I'm pulling the equilibrium on the left-hand side, that means this BH must release. It gives up a bit more of that proton. It goes down, that's right. If I react some of this to make up for that hole in this equilibrium, Le Chatelier says BH plus has to go down, which means the B concentration must go up. If we do the reciprocal, if I were to add protons to this solution, if I was going to add acid to the solution, I'm increasing, adding more of this. What happens to the equilibrium? Goes to the right or goes to the left? It's going to have to go to the right. The B concentration goes down, BH would go up. So the conjugate acid-base pair is really acting like a spring. This is what we mean by like a battery. Having both enough, what we say is an appreciable concentration. We mean there's enough of it dissolved in solution. If I have both of those in solution, then what's going to happen is the base, the B concentration will drop and the BH concentration will increase, or vice versa, depending on if I'm adding an acid or base to the solution. This equilibrium is critical because it helps to sort of push and pull, where overall the H3O plus concentration does not change very much. As some of it reacts, the conjugate acid will give up that species. So it's trying to hold it in this invariant way. Now, important thing about buffers. Having a buffer in solution just means the pH does not change according to external forces. It doesn't mean it's always neutral. It could be the buffer or the pH of the solution, depending on what those two species are, will be set at a certain level. In biology, in blood, the pH of our blood has to be maintained. Does anybody remember what that number usually is? pH of blood, for at least if you're all good and healthy, is about neutral. So the ions, the particular acid and base that is in solution must have a sort of a pKa balance in and around that range. But you can set up a buffer whose average value, the held value, is down around 2. Or you can set up a buffer whose value isn't around 10. It all depends on which HA and A minus you choose to use and their relative equilibrium constant for these ones. The pH of the buffer depends exactly on the pKa of the weak acid you happen to be using. That's why different acids of different pKa's can be used to set buffers at different strengths. The important thing is you must have this conjugate pair, and they have to be related to each other this way. The proton is either being sucked up or dropped off between these two. All we end up doing is changing the ratio between these two. But overall, the H3O plus concentration relatively remains constant. Now, it's not perfect. It will vary slightly, but it's not like an acid-base titration where you get this rapid change between the two. If we did not have this, life would be exceptionally difficult. Does anybody know what happens if you take proteins, most of what we're made of, and you suddenly change the pH? Who's taken like an egg and put vinegar on it? Because that sounds delicious, right? Yeah, it blows apart. So the reason that we're stable, homeostasis in our blood, is possible because any large swings, if you suddenly drink a bottle of cola or vinegar if you chose, your pH in your blood does not change significantly. Buffers in your solution are helping to hold that pH about constant. So it's always going to be a mix of a weak acid and the salt or conjugate base. So it's always going to have these two components. So for an example, we have acetic acid plus CH3COO minus. That's the business end of the molecule that matters. The salt thing here, this here, if you see that I dissolve acetic acid and this component, the thing that we have to focus on is the conjugate base of this acid. The sodium is a spectator ion just coming along for the ride. It does not affect the pH of the solution. Likewise, if I have a weak base, ammonia and ammonium, the weak conjugate acid, that is my conjugate acid-base pair that's resulting in this buffer. What happens is we can make a buffer by either taking either of these components, so I physically weigh out an acid and its salt, or a base and its salt, or I can take a weak acid and some strong base. Remember, again, look at that first example. If I took acetic acid, 1 mole of acetic acid, and I add half a mole of sodium hydroxide, how many moles of acetic acid must I use up by taking 1 mole of acetic acid, half a mole of sodium hydroxide? How much acetic acid did I react? Strong base with a weak acid, Which way does that work? Yeah, the strong base will completely eat up however many moles of that weak acid I have. 1 full mole of acetic acid, half a mole of strong base. What's going to happen there is I'm going to use or react some of that weak acid, leaving behind some, but forming my conjugate base. It's a way of reactively making a buffer system. So if I start with only one of those components, only weak acid or only weak base, and I add a strong component, I'm creating the necessary acid-base pair in the concentration I'm doing. So these are the 4 unique experimental ways that I can create a buffer, either by adding the 2 needed components or starting with one of them and adding a strong component to do that reaction in situ. So what we're going to work through now is a series of different calculations where we're going to measure what is the pH of a solution, starting from strong acids or weak bases or any combination thereof. And most importantly, we're going to calculate using a couple key sort of equations. Now, does anybody know where we're going here? Do you remember the name of the equation that we're using to help do these sort of calculations? It starts with 2 dudes, both with an H. Yeah, this is the Henderson-Hasselbalch equation, right? So again, for anybody who's seen this before, this is where we're going to be applying it for this one. The important thing is this last part here. To define a system as a buffer, the Henderson-Hasselbalch equation is useful for calculating the pH of that solution given some ratio of base and conjugate acid or acid and conjugate base. The important thing is it has to be within this ratio of the conjugate acid base, their relative concentrations, needs to sort of be within this kind of factor of 10. In other words, this last point here is really important because it sort of defines where we are allowed to use CAB, conjugate acid base pairs, is what I mean by CABPs. So if I have something where I have an acid and in this equilibrium it's conjugate base, for this to be a buffer, the ratio of HA relative to A minus, it can range from 10 to 1 or 1 to 10. What I mean is that's a factor or a multiplicative value of their relative concentrations. This amount, where if I have 10 times as much weak acid as I do conjugate base, or 10 times as much conjugate base relative to weak acid, this range is what we call our buffering region. The reason why is if I start going beyond this, if I had 50 times the HA relative to A minus or 50 times A minus relative to HA, it's not going to act like a really good spring. If you imagine this, remember the whole purpose of this is if I were to add H3O plus to the solution, adding this will tend to push the equilibrium this way. Well, if I only had, let's say this happened to be a 50 to 1 ratio, there's not very much of this around. If I have a ton of HA, tiny little bit of A minus, and I suddenly add a bunch of H3O plus, this cannot effectively balance because I need to use up A minus to make H3O plus. And if there's a lot of this, tiny bit of that, it will not act like a buffer. That's why we define these regions of 10 to 1 to 1 to 10. That's also what we're really saying is mathematically, as far as the Henderson-Hasselbalch equation goes, that's the type of region where the Henderson-Hasselbalch will actually apply. So this is how we define or derive the Henderson-Hasselbalch equation. We start, now first of all, that first equilibrium, does everybody recognize that? We had a special name for that equation up at the top. Oops, why can't I get over there? What is the name of that HA plus water giving A minus? Yeah, that is the Ka, or the acid dissociation equilibrium equation. Which means if that's my equilibrium I'm considering, remember I can define the Ka of that. That's products over starting materials. That's the first step in our derivation shown right here. Next, I can define, as we've talked before, the pKa. That's taking the negative log of that Ka value. So that's what we're doing here. We're taking the negative log of this side of the equation And this is that the ratio form of our Ka expression. If I take the negative log of all this, this is the species I get over here. Now remember, if I'm going to take a negative log of some fraction, I can actually break this up into different factors. So this overall equation can be split into negative log H3O plus and negative log of A minus over HA. So last step is if I have these two, this is another factor, another equation that we've seen before. Negative log of H3O plus is also known as the pH. And finally, minus log of this A minus over HA, that is the ratio of the conjugate base and its acid for some system. So this is how this is the Henderson-Hasselbalch equation. It will be one of the ones that's definitely on your formula sheet, but the thing to remember, right, if we go through this, pKa, you guys should all know that. That is the negative log of the Ka. The reason I know it's supposed to be minus A minus over HA is because A minus is a product that's in the product part of my term. The ratio must be A minus over HA as defined by the Ka expression. The other way to draw this is, have you seen a different form of the Henderson-Hasselbalch equation? That's the only reason I want to state it. Some people may draw it or are used to seeing it with a different sign or different components. Like we're showing, yeah, we can do with POH, right? pH could be converted to POH. How do you guys do that? Do you remember how to do that? How do you go back and forth between pH and POH? What's the relationship between them? Yeah, pH plus POH equals 14. So that's one way. You could invert pH to POH. What would happen to that last term if I wrote that as instead of A minus over HA, what if I write it upside down? HA over A minus. What happens to the sign out front of it? Yeah, it's a plus log now. So inverting that last one, putting the conjugate base on the bottom and the acid, the HA, on the top of that ratio would change the sign of it. All those are similar mathematical permutations, and depending if you've seen different pieces, same equation. These are not different equations, they're just different representations of common factors or values. The other thing too is, remember, pKa, there's one more value for every acid-base thing. pKa can also be related to what? pK, just like pH can go to POH? Yeah, PW. PW is a constant. Yeah, a pKa can be converted to a pKb value by using the pKw. So these are different transpositions that you can imagine that you could walk through. Again, I just mentioned them because working through that different part of it, you can get different sort of sets. The final Henderson-Hasselbalch usually is written this way, where we put the pH of the solution out front and then the pKa in between. And as a result of that, algebra says we move that negative log on the other side, we get pH equals pKa plus log of base over acid, right? That is the usual sort of expression you see. But again, algebraically, they are all related this way. The pH in this equation is the measured pH of the solution given some specific concentration of A minus and HA. So what usually we're trying to do is either given the pH and a pKa, figure out what that ratio should be, or given a ratio and a pKa, what is the pH of this solution? So we're going to work through a couple of these common ones now. All right. So first off, I'm going to work through about one or two of these longhand. I have a separate video going through the entire deck, walking through all of the problems, and your baseline sets have an entire different series of these equations. The calculations we're walking through are every sort of category of question that you would normally run into on the acid-base assessment. So this is why we encourage you to do it. There's only a certain number of ways we can ask these kinds of questions. The permutations end up being very similar, right? So the most important thing is to test, how do I do this particular setup? And what you'll see is that there's a sort of common sort of lineup to these questions. So practicing the different types and how their approaches will give you sort of the ability to do any kind of question this way. They're going to be written out longhand as well, so we have the full sort of step-by-step shown with work that will also be online. The assignments for acids and bases, this is an assessment. The assessment is on Canvas. It's on the main Canvas page, and it should be launched now. It should be available to this one. Yeah, exactly. Okay, so let's work through this first problem. All right. So we've been given a solution and we're being asked to calculate the pH of a solution of benzoic acid. So by that name, benzoic acid, this is some weak acid in the solution. So benzoic acid as drawn, C6H5COOH. That is an acid. I am going to term that HA. This is my weak acid component. I'm adding it to solution. So this is my HA species that I'm adding to this one. Again, it is an acid. That's why I'm calling it, the benzoic acid is my HA part. It's being added to water. How much water? 100 milliliters. The HA, more importantly, I've got a value. I have 0.002 moles of benzoic acid. I'm also given one more important piece of information. The pKa of benzoic acid is equal to 4.20. Okay, so number one, what is this information telling me? The pKa is about 4.2. What does this sound like? Weak acid, strong acid, acid at all? Yeah, it's acidic, right? It's down below 7. And weak acid, right? In around that 4 or 5 thing, that is a weak acid one. Strong acids, pKa would be much closer to 0, down close, much lower, right? So that numerically is something you want to pay attention to. So these are the bits and pieces. The equation I'm really talking about here is I'm adding HA to solution, to water. Now, if it's a weak acid, I know how much HA I'm starting off with. I'm putting it into water. Some of that acid will dissociate, right? It will form my conjugate base and H3O+. And it's this value right here that I'm after. That's how I'm going to get my pH, right? Because if I know the H3O+ concentration, I should be able to calculate the pH of this solution. The problem is, I know how much HA I've added. I put it into water. Will all of this dissociate? If this was HCl, strong acid, all of it's going to dissociate. The concentration of the acid I'm starting out with will equal the concentration of H3O+. That's only true with strong acids. Not all of it's going to dissociate because we have a weak acid. This is going to be an equilibrium. What do we know about weak acids? Starting material favored or product favored? If this is a weak acid, it's reactant favored. That's right. What about the Ka value? Bigger than 1 or less than 1? Yeah, less than 1. Starting material favored. Okay, so we can do this. Now what we have to do, though, is figure out, given some Ka value, we know the equilibrium constant, and the concentrations we started off with, what is the concentration of H3O+ when this thing reaches equilibrium, after we've sort of set up that? So first thing I'm going to do, I need to know the initial concentration. Initial concentration of my HA component. All right, well, I've got that. The concentration of any species is the number of moles over the volume, which in this case, 0.002 moles over 0.1 liter, right? Yeah, ice tables, exactly. So the initial concentration for this guy, I get out concentration of HA initial is equal to 0.02 molar, capital M, moles per liter. Okay, great. That's the starting state. That's the HA that I added. Now remember, we talked about this concept last time. If I take HA, benzoic acid, I know the concentration. Initially, is the system at equilibrium? So imagine, here's my beaker. I'm going to chuck in 0.002 moles of HA, and I've got a solution here, or water, that's 0.1 liters. The second that those two guys go together, this is not equilibrium yet. This is the initial state. Does anybody remember the value, the term we gave to measure, Q, exactly. This is not K. The instantaneous concentration or the reaction quotient would be how much stuff do you have in this equilibrium before it has reached equilibrium. So this is our initial state. That's why we call this, so let me quickly redraw this. We're dealing with the equation, HA plus water in equilibrium with A minus and H3O plus. This is what we called the Ka expression. And we have some initial value where if I was going to write out these concentrations, we just calculated this as 0.02. What's the initial concentration of water? Yeah, do not include water. Remember, what is the concentration? And for me, different people may be used to different sort of ways. I always use concentrations in my ICE table. The reason why that's important is because if I use a concentration, I'm dealing with balanced equilibria that immediately relate to my Ka expression. Remember, Ka is concentrations of products over concentrations of reactants. You can do it with moles too. Just be really careful about the volumes that you are dealing with, okay? So I, by definition, usually will convert things to moles, and I'm dealing with the concentration values. My initial concentration of HA is 0.02. Water, I don't have a concentration. If I'm assuming that I start this thing out, initially how much A minus is in that solution? Yeah, nothing. Goose egg. How much H3O plus is in that solution? Goose egg for this guy. It's neutral. There's a tiny amount of it, right? The ionization of water, we're going to neglect that. We're saying that I'm starting off with a solution where it's pure HA, no A minus, no H3O plus from this expression. That's right. Then we have step 2, the change. Which way is this equilibrium going to go? To the right or to the left? If I only have HA, it's got to go to the right, meaning I'm going to lose some amount of this. Again, don't care about water, and I'm going to gain some amount of A minus. Most importantly, for every mole of HA I lose, I gain the equivalent number of moles of A minus and H3O plus. So whatever moles here, I'm going to gain these two. The sign and values are going to match up. Last is your equilibrium position. At equilibrium, it will be your initial minus your change. Again, water we're not paying attention to. This will just be X and X. The equilibrium value is the algebraic form of how many moles, or what the concentrations is, after it's reached equilibrium. So now we have an expression with a single unknown to solve. That's awesome. How do we relate? Does anybody know? What's the next step? Great, I've got an expression here with X's in it. How do I relate these concentrations to each other? Plug into equation, the Ka expression, that's right. Ka is equal to concentration A minus, concentration H3O plus over the concentration of HA, which we've just given those things values. That's X, X, and 0.02 minus X. Boom, great. That's awesome. How do I solve for X? I have 2 more problems here. This is x squared over 0.02x. So everybody immediately grabs out your quadratic equation, right? And starts to solve for, because you got a thing, and that doesn't work, right? Like there's a problem here. If I had to sort of express this, sorry, let me rewrite that. This is actually x squared over 0.02 minus x, right? It's a complex polynomial. That's not super cool. Having to do the quadratic equation is not necessary because we add a simplification to this step. That's one. Second thing too is, what's my value for Ka? Go back to your question. Were we given Ka? We were not given the number. Yeah, but it's encoded. It's in the pKa. So there are 2 more steps we need to do. first. We have pKa, not Ka. The pKa was given as 4.20, which we can convert. Remember, pKa is equal to minus log of the Ka, so therefore Ka is equal to 10 to the minus pKa, or Ka here is equal to 10 to the minus 4.2, which equals 6.31 times 10 to the minus 5. That's the first one. Again, gut check, and this is a really important thing when you're doing your calculations. What did we say about benzoic acid? Weak acid or strong acid? Weak. What does that mean about the value for Ka that we expect? Bigger than 1, smaller than 1? Does that match here? Are we smaller than 1? Boom. If you do this and you end up with a Ka of 6 times 10 to the 50, something has gone drastically wrong. Go check your work, right? So always walk through your physical constants and, again, walk it through what you think is happening. All right, last step. We now know 6.31 times 10 to the minus 5 is equal to x squared over 0.02 minus x. And yeah, guys in the chat, you picked it up. We can neglect this x value. Why? What is the rationality we can do to that? Yeah, it's approximately equal. What we're saying, remember, is this equilibrium, the Ka we're talking about, very little of that will become products. X is your product. Most of it's going to want to stay as starting material. So because most of it wants to stay as starting material, X is going to be a relatively insignificant value. It's not perfect. You're right. To be analytically accurate, we'd have to go through and check it. But what we are going to make the assumption, at least initially, is it is approximately equal to x squared over 0.02. We can neglect the value for x, and there's two reasons we can do that. It's a weak acid, it is starting material favored, and second, the concentration that we're dealing with, 0.02, is very large relative to that x value. So now we can solve this. Punching through, grind the last of it. Does anybody have an answer? So 6.31, 10 to the minus 5 is equal to x squared over 0.02, which I get as x squared is equal to 1.26 times 10 to the minus 6. X equals 1.12 times 10 to the minus 3 molar. Ish. And then we celebrate and run away and we're done. Right? What's missing? Yeah. Last step, and I want to put a pin on that too. Emphasize that. Always go back and look at what you did in the question. So many times you get to this point, you're like, wow, that was a journey. I'm so happy. Let's move on to question 2. You are not done yet. This, X is what? X is the concentration of H3O+. It is not the pH yet. So negative log of that value is, I'll put it up here, pH is equal to 2.95. Perfect. Where did 6.31 times 10 to the minus 5? That is your Ka value, comes from right here. It comes from your pKa value that we were given. Okay, last question about this. Is this a buffer? Hell no, I agree. Why? What is your justification? How do I say this is not a buffer? No, there's okay, remember, buffer has to have HA and A minus. Oh yeah, well we have A minus, we have HA. Well, okay, neutral solution when acidic, that's not so bad, right? Remember, buffers can have any pH value they want. To be a buffer, yeah, just because it's low pH is not a thing. We may have formed a buffer, right? But what makes it a buffer? What's the definition we just talked about? All buffers must have, both. You need, remember, a significant amount. So to be a buffer, you have to have HA, A minus. What was the ratio, the buffering range, the relative amount of those two that I needed to have? Yeah, within either 10x and 1 or 1x and 10. If you look at the amount we have, H3O plus concentration, 1.2 times 10 to the minus 3. What is the approximate concentration of HA? 0.02. You have 0.02 and you have this tiny, tiny little number. That is way outside that buffering range. There's also one other way to look at it. We say for a buffer, the pH of the solution is either plus or minus 1 relative to the pKa, of the acid. What was the pKa of this acid? pKa of the acid, 4.2. pH of the solution is 2.95. We are outside the buffering range when we look at the pH is plus or minus 1. So for this acid, whose pKa is 4.2, our buffering region could be as low as 3 and as high as 5. 3.2 to 5.2. We are 2.9. We are outside of that range. That's one way to check it. The second is this. The absolute value of our acid and our base is outside of this 10 to 1 or 1 to 10 kind of range. Why do we exclude X? Because the dissociation, the amount that we do, we start and assume that it's going to be small. It simplifies the calculation, and again, it's appropriate because we're dealing with a weak acid whose dissociation generally will be small. We can do the same thing with the weak bases. All right, guys. So I finished this part out right now. This is the longhand of this one here. As I said, I'm going to post the video walking through each of these longhand calculations, talking through the same sort of point of it. But this is how you do the rote calculations of your buffers. We'll take a review of this on Monday. Please, over the weekend, take a second and watch through those videos. But again, the questions that we have, these different sort of stages, they map out every kind of acid or base question that you could see. Right? So watching through these, practicing these parts, and then trying the acid-base assessment, that will give you every composition and combination that's going to be necessary. All right, guys. I hope you have a wonderful weekend. I'm happy to stay around a little bit and answer any questions. Again, really happy to have you guys for week 1 and looking forward to next week. Have a great time. Theo.
It's just Theo.
Sorry.
But so we could